Welcome to all the learners. So I welcome to this live class of computer architecture, and today's topic is SIMD architecture, which belongs to unit number 10 of your curriculum. Now, in the previous week, we have earlier gone through the memory architecture part, and we have gone through a very detailed understanding of memory structure. And after that, we have studied about the use and effectiveness of vector processors. So this is in continuation of the previous two, what we have understand the sessions, and let us go through from where we have work out on different memory aspect as well as different examples of vector processor. So I'm Dr. Santosh Kumar Vishwakarma. Welcome again, you all, and let us go through the contents. As already Flyn's classification we have covered in the very beginning of this course, and it was unit number 2, where we have learned about the different classifications, okay, of parallel systems. So single instruction multiple data, in short, which is known as SIMD. It is one of the several approaches to parallelism found in modern high performance computing. And this has been very feasible. That's why we are learning it in a separate aspect, and in continuation of memory as well as vector processor also. So as we'll go ahead, we'll see different types of SIMD processes architecture, and we'll also learn about what about the design issues of SIMD in terms of architecture perspective. So the learning objectives are, we'll discuss the concept of data parallel architecture. We'll also describe the SMID design space in terms of hardware structure, as well as we'll take few points about the software configuration also, once we are going to have the parallel structure in working with different algorithms also. We'll also see the types of SMID architecture, and we'll recognize the fine-grained SIMD architecture, as well as you'll be able to explain coarse-grained SIMD architecture. All right, so let's begin the session. Now, what I said that first of all, we need to have a clear picture about the design issues. Okay, so what are the design issues once we are going to achieve this SIMD architecture? So I will come up with certain questions, and these questions are related to each of the parallel structure that we may have. Either it is SIMD, or it is SISD, or MISD, or MIMD. We simply need to have a thought on this, that what should be the correct version of all these questions that we may replicate once we are going to achieve the parallelism. So let me start with the first point. How do you exploit concurrency? I hope all of you clear with this word concurrency. So when we execute multiple processes, okay, when we execute multiple transactions, so we achieve concurrency. And obviously concurrency comes with number of advantages as well as number of challenges also. What we have discussed, that we may come across number of conflicts because the common resources, common data has been shared among multiple processes. So how do we exploit concurrency? Define as parallel updates to data, very important point, without specifying in detail how this concurrent execution is implemented. So this is one of the very important remark that must be answered once we are going to have the solution of parallelism in any of the structure. So students, if you feel any questions regarding whatsoever topic we are going to discuss today, you can just raise your hands, and I will have, I will just see if there is any doubt or question, and will be happy to answer that also. Now, the first point is, although the order is not important, but as per the slide, the first point is scalability. And scalability, it means that how many processes can the parallel program effectively utilize. Okay, if we are talking about in terms of implementation issues, so we need to be very particular about what is the number. Okay, how many processor, and is it scalable? Can we extend that? That is very important part, because if you can come up with one of that architecture and that has been limited to a specific program, so the scalability features always goes down. So you need to have a very clear understanding whether it is open for the other programs, whether it's open for other processes also. Now the scale, as you can see in the second point, the scalability of a program is restricted by 3 factors. Okay, so the first factor is This one, amount of concurrency available in the algorithm. Very important point, because we have implemented the algorithm. As we have seen that there may be different distributed environment, there may be different variables, different methodologies. So it's very important that what is the concurrency, granularity also, okay, available in the algorithm. Now, fraction of the runtime spent during inherently serial work, and then parallel overhead of the algorithm. So these three are very important factors by which we can determine whether the given algorithm is scalable or not. Apart from that, we may have some other goals like the target hardware platform, because if you are talking about the architecture part, obviously we need to have a reference of both or the same topic. When I discuss about the memory management, first of all, I have taken a brief discussion about in terms of software, in terms of operating system. We understood the things, and then we have explored the computer architecture perspective. So same happens over here. We need to understand first of all this software category and then also the hardware part. So what constraint exists on the maximum number of processing elements? So amount of exploitable concurrency is large enough, serial fraction of the code small enough, and overhead small enough to allow the algorithm to make good use of whatsoever processing elements are available. So apart from this, if you just explore the things that, like suppose if you are working with a distributed environment, okay, and there has been lots of processors, they have been simultaneously executing a single task, or different task which has been threaded also. So the thing is that serial fraction of the code, is it enough or not, or what is the overhead allow for all that switching case which is required once we transmit the result after one clock cycle. So apart from scalability issues, some design issues are like efficiency. Let me go through this part, that how close does the program come to fully utilizing the resources of the parallel computer. Okay, so again, this point rates towards the software aspect, that if you are going to have the parallel computers, if you are going to have multiple processors, so what about the program capacity in terms of utilizing? I will just give you one very simple example. Like suppose we say that CPU, okay, is one of the important and core of the everything resources. Now, once we have operating system, and once we are operating system executing, okay, the different programs, different applications, and obviously CPU is the core of everything. One of the important criteria of OS performance is that whether it is capable to execute the CPU to the maximum. So we understand that the maximum utilization is 100%. Do you feel that we can utilize the 100% capability of CPU? Okay, so obviously what you are thinking, I have the same answer, that the answer is no. So that's why we go through the maximum. What's your maximum we can utilize? And I hope so that you are not having the answer 100%, because it's next to difficult that we can have the 100% capability. Okay. Now, efficiency is typically measured by comparing the time taken by the best sequential algorithm to the time taken by the parallel algorithm, multiplied by the number of processing elements. So by this, you can just find out in what terms we are going to define efficiency. Now, the next point is maintainability. So is the program easy to maintain? And what does it mean by maintain? It means it is easy to debug, verify, and modify. All right. So again, why I'm talking about program? Because you must understand the software aspect also. So programs that are difficult to understand and are usually also difficult to get running in the first place and to modify their lifetimes. So parallel programs are difficult to debug if programmers cannot understand them without reasoning about multiple independent threads of control interacting in different way. I hope you understand the last line, that if you're working with a single program, all right, and this program is working with different processors in a different environment, okay, so it's a very difficult task that in a single cycle, if they are executing a thread of one of the program, how they are going to connect, how they are going to merge. So it's a very typical, very challenging issue, that how to write program which have distributed locking and distributed control. Even this is, it has been a single system. Okay, if suppose there has been a single system and the resources are common, like suppose there's a resources X which has been shared by P1 and then P2 itself, there may be different conflicts, and there should be a proper ordering that when to read and when to write. Same happens with this over here, but this is quite in a bigger level, that how we can perform in terms of software category, the things is going to be smooth without any conflict, and it should achieve the concurrency aspect also. We also come to the very important point, environmental affinity. So is the program well aligned with the programming environment and the hardware of choice? Okay. Whether feasible program design should be portable to as many platforms. So portability is again, one of the core of the issues. But in any case, it should be possible to implement them efficiently on likely target platforms. Now, it is also desirable that the result of an execution of a parallel program, okay, be the same regardless of the number of processing elements. What does it mean? It means that if we are a single task has been distributed among multiple, processors for simultaneous executions, so we must have that category of results that every clock cycle it may have be able to produce the things, okay, the results. So it's not possible always, because changes in the order of floating point operations can produce small, okay, changes in results. So this seems to be a very difficult task, and see, let us explore how the things is going to be manageable in terms of writing codes. So the solution is, it's desirable that allows to reason about correctness and do most testing on a single process version of the program to maintain the integrity, to maintain the effectiveness. So in short, we have discussed about few design issues, and let me repeat this. Do you have any question on any of this? Although many of the points I have not covered, because this I was talking about in terms of software perspective for working with the parallel system or the concurrent executions. So we have talked about the scalability issues. We have talked about the code fractions issues, the code concurrency, and how the algorithm can be effectively utilized. Then we have discussed about efficiency, very important part. Next is maintainability, and next is environment affinity. Okay, so before I shall go to the recap of the previous session, this I want you to spark on. Okay, this I want you to trigger on, because computer architecture should not be treated as only a standalone structure. That's it. No, you must be accompanied the same with how the things are going to happen. So that's why this, I hope this point may trigger you, that if I will come up with any of the architecture like SISD or SIMD particular in this session, so you must be thought about that, how the things are going to be cope up with any of this issue. So before I shall go ahead, I will check that any of the students have any doubt on any of the point which we have discussed, so we can have a discussion on that. Okay, so any attendees or any learners, if you have any questions, so you can just raise your digital hand, and I will love to take your question. Okay, so Usha Chaudhary, I will just make you the presenter. Yes, Usha, you can unmute yourself and you can speak out. Usha Chaudhary, I am audible? Okay, so I think my voice is not audible to her, or might be she's not able to unmute. So yes, Abhishek, welcome, and I will just give you the opportunity to talk about the same. Make a presenter. Yes, Abhishek ji, you can unmute.
Hello, good afternoon, sir.
Yeah, good afternoon, Abhishek.
Sir, what is parallel algorithm overhead?
Yeah. So, there is not a single terminology which we can speak out of this your question. So parallel algorithm overhead consists of lots of things. Number one is, suppose if you are going to share the common variables. So common variables, every variables has a distinct state, have a distinct holdings. and this variable is going to be shared among multiple, in a global scenario, it's going to be shared among multiple processors, okay, multiple tasks, multiple processes. So one of the overhead is that how to keep track of that. Like suppose if you, Abhishek ji, if you can remember in operating system, once we have say multiple processes like P1, P2 and say P3, so we keep track of each and every processes, and that itself is a overhead in a single system. If you talk about Unix or Linux, same happen over here. If you are working with the parallel algorithms, you need to keep track of the variables assigned, the memory part, the thread sections, the timing issues. Everything can be considered as a overhead.
Oh,
Yeah.
thank you.
Okay, so thank you, Abhishek, for your question. I think there is no such other questions, so I will go we'll go ahead, and after 15 minutes again I will check it out. If you have any other questions, we'll speak it out. Now this is just a recap what we did in the previous session. So one of the aim is that computer that can solve mathematical problems, so arithmetic operations on the large array of integers or floating points number quickly. Okay, so there may be two options. One of the options was either you can go ahead with the traditional implementation part, otherwise you can just go through the vector processing operations. Okay, just now we have gone through this partner that overhead. So I have speak about this thing, and you can also see that we have also discussed in the previous week that overhead of processing loops and fasten the computations. So parallelism must be introduced, and obviously once we started with parallelism, there comes another major issues what we have gone through. So we in the previous session we discussed about the vector processing, that it's possible only if the operations perform in parallel are independent. If there has been dependency, like suppose AI depends on the BI and BI on CI, then obviously this will not be achievable. So in support of that, we have gone through a few numerical questions also. Like suppose if you want to add two numbers, that is scalar R1 and R2, and you want to add this and store the result into R3. So that can be very well done if it is a scalar part. And for vector, we need to have that kind of array length also. So we have discussed about the vector length, how it can be done, and how the different instances can be achieved once we have this same operation. So vector processing operates on all the elements of the array in parallel, providing each pass is independent of the other. And we have also explored that vector processing avoids the overhead of the loop control mechanism that occurs in general purpose computer. So this example was given to you, and I also will refer the same for today's section, that in general processing, if you have to add this a plus b, and there has been 10 iterations. So you will read it out and decode, fetch the ith element, and then add. You will store the result in C, and this is iterative. You will execute it 10 times, like suppose in the loop structure. So for I to 10, you'll execute the same, and every time it will be incremented to 1. Like from 1 we have started, then plus plus, so it will go to 2, then it will go to 3, and so on. So this is a general processing system. But if we have the system supporting vector processing, so we can do it in a single instruction cycle. So read instruction and decode, fetch all the elements of AI, assuming that they are independent of each other. We can fetch all 10 elements of B, and we can have a summation over here. So already we have covered this example just to have the reference, because today again we are going to refer this kind of example. So you must be very clear that this is for scalar and this is for vector processing. Now we have seen there may be 4 major functions or features of vector processing. So one, if input is vector, now the second may be vector, means I have taken this example for the complement. Now if suppose we want the maximum, if there has been vector elements and we want maximum element, that will be scalar. So V2S, one of the example of that, V2S. Now, if the third was v into v, so the result will be v, and when vector into scalar, we come to v. So this has been done in the previous session. I hope all of you have been attending the sessions, regularly. So you can just refer the videos and you can see the different examples that we have seen. I am talking about this in this session, because when we talk about the SMID structure, you need to be clear about, you need to have an understanding, okay, how the things are going to be executed in terms of this vector processing and other examples also. So we have also discussed that the 4 stages are identified in the development of parallelism. First is the algorithm itself, second is the language, third is the object code, and the target machine code. And in the ideal situation, the parameters are supposed to be in this order. What is A? So the parallel algorithm are higher than L, that is high level language, is higher in terms of O, and it's higher in terms of target machine code. So this is one of the ideal condition which we have explored once we have completed all this topic of vector processing. Now, because we are going to learn SMID, so be very particular about single thread versus multi-thread processes. So this slide has been captured from the earlier unit, okay, where we have discussed about the different parallel as well as concurrent and some sort of serial systems. So if we can have a single thread system which may be part of a process, okay, so suppose there's a process, and generally process is defined as program and execution. So if there's a process which may have a single thread, so that is known as single threaded process. Now if the process may have multiple threads, okay, so that may be multiple thread processes, and obviously thread can be defined as a piece of code which itself may have, like suppose this thread may have its running code, its registers value, and its stack value. So this, once we implement the system of multi-threading system, so it comes with lot of advantages that can be very well understood, that can be very well captured once we are going to execute in terms of parallel structures. What is serial execution? As you can see, and this contents, you can find it out from your notes which has been provided to you, that serial execution is CPU, and these are the various tasks, that is T1, T2, T3, and so on. We have the problem, and now we are going to have that instructions I. So if like CPU is executing the task one by one, that is serial execution. T1, after finish of T1, T2, so there is no overlapping, right? There is no context switch. It's simply like first in, then completed, and then second in, second completed, and so on. So this guarantees that result is correct, right? Working with serial execution, provided that result will be 100% correct, because there is no conflict, there is no conflict, there is no overlap, there is no overlap. But in terms of speed, in terms of efficiency, in terms of throughput, it has to give its value, okay, because throughput will be low over here. What is throughput? That is number of processes or number of tasks completed per unit of time. So obviously that will be quite less with compared to the other system. So that is the serial executions. Now let us see the parallel execution. So there's a problem which has been worked like this, that this T1 task has been distributed among multiple CPUs. Okay, so a single task has been classified into small tasks. We also say it is normalized into small sections, and then that can be given to CPU for further processing. So this example of parallel computing quite better, because here if you talk about the throughput, so definitely it's going to be increased with compared to the previous version what has been shown to you. Now let us see the concurrent execution. Very important phenomena, very important. Now because let me go to this point, and then we'll elaborate with all the merge algorithms also. So concurrent execution is the temporal behavior of n client one server model, where one client is served at any given moment. Okay, so yes, there's a single CPU and there will be multiple thread, but you can see the efficiency of the CPU. Okay, the CPU is not sitting idle. Once this task has been done, okay, so it may go ahead with the second thread. It's not like that, that there's a single program only. We can have different other programs, but once this is done, it will move to the second one, then next come like this. So this is like what? That N client, we are just serving multiple clients, multiple threads, and there's a single server model. So in this situation, the key problem is how the competing clients, let us say processes or threads, should be scheduled for service execution by the single server. Okay, that is processes. So it means that it's a one CPU serving multi-thread systems. All right. But as you can see, it consists of benefits with compared to the serial execution, where only one process was there into the system. Here we allow multiple processes or multiple threads, but CPU is executing as per the, once this executed part, it will move to the second and so on. So yes, utilization of the CPU is quite higher with compared to the previous serial version, but we need to incorporate in such a manner that we should achieve, the benefits of parallel as well as concurrent executions. So the scheduling policy may be viewed as covering the following two aspects. Preemption rule. So it deals with which servicing a client can be interrupted or not, if on what occasions. Very important point might be you have also learned about the pre-scheduling algorithms in operating systems. So preemption is very important, like which to preempt. Preempt means which task or which process is going to be stop in between. That is preemption rule. And the second is selection rule. So it states how one of the competing clients is selected for service. So the selection rule is typically based on certain parameters such as priority, arrival time, and so on. Now we'll come to the most important aspect of today's session, the parallel execution. So what is parallel execution? It is n client and server model. So it's very clear that it's going to have a embedded everything that we have seen in the previous slides. So it has multiple CPUs, and we are going to be benefited with the previous model where we have only seen one server and multiple clients, like just now in terms of concurrent execution. We have seen this diagram, and now we are going to impart multiple CPU. So we come up with the concept of this, that there may be n client and n server model. So having more than one server allows the servicing of more than one client at the same time, and this is called parallel executions. So parallel computing is the simultaneous use of multiple computer resources to solve a computational problem. And obviously we are going to have multiple CPUs, and a problem is broken into discrete parts that can be solved concurrently. This architecture is the parallel concurrent execution. As you can see, we have two servers or two CPUs over here, and they are just serving, task 1, task 2, task 3, task 4. So in parallel, you achieve the concurrent execution also. So this is a true parallel concurrent execution system. So again, referring to again the same content what we have discussed in unit 2, that according to the client's classification, we may have data streams 1 to many and the instruction stream 1 to many. So if it is 1 to 1, it means single system and single instruction and single data. So that is the first part. And today we are going to explore about this, that based on a single instruction, how the system are going to support with many data stream. So I repeat, that is single instruction, multiple data stream. Now let us see the different aspect of SMID. So point number 1 is that this SMID, they are terms as vector instructions. And what's the reason? Because it's a single instruction and multiple data. Okay. So operating on multiple data in just one instruction is very important, and this justify the definition itself. you are going to operate, or the system or the structure is going to operate with multiple data, and the instruction is going to be same. So that's why the name given single instruction and multiple data. Now the data for vector instructions are stored in vector registers. Each vector register can store several data elements at a time. And the very important, this several data elements in vector registers is formed as vector operand, which is used for further processing. And as you have seen that there has been a difference between the supercomputers and the vector processing. So vector processing supercomputers are also capable of doing scalar processing. And later, array processor was introduced, which was particularly deals with vector processing that do not indulge in scalar processing. So if you can see that although we have very much discussed about the scalar and vector processes in our previous session, so SMID mostly is going to support the vector registers in terms of the vector operands, which are possible once we are going to have the several data elements. And obviously this is a need, because until and unless we don't have that kind of structure, we cannot solve very efficiently the floating points algorithms. Let me elaborate all these points, and then we'll see the structural view of SMID structure. So this SMID represents an organization that includes many processing units. Soon we'll explore the diagram itself under the supervision of a common control unit. Okay, we'll just take 30 seconds. Okay, so coming to the second point, all processors receive the same instruction from the control unit but operate on different. So that is the more significant part of SMID, what it justifies the name itself, that if we are going to have many processors, if we are going to have multiple CPUs, so the I is going to be same, instructions is going to be same, but they are going to operate on data 1, data 2, data 3. That is, the main code part of working with SMD structure. Now, the shared memory unit must contain multiple modules so that it can communicate with all the processors simultaneously. Okay, one of the overhead also, because if they have their local memory, then obviously in the shared part, they come up with the outcome of the every clock cycle. Pipeline processors and superscalar processors are common examples found in most modern SISD computers, and instructions are sent to the control unit from the memory module and are decoded and sent to the processing unit, which processes on the data retrieved from memory module and sends back to it. Let me explore the next diagram where you can see how the things are going to work. So this is one of the example of SMID structure, which stand for single instruction and multiple data stream. So there's a memory, and that can be taken as one of that shared memory, and there's a control unit. So different, as you can see that we have different CPUs over here, different processors over here, and they have been in an alignment network. And if we keep the memory module also, then definitely whatsoever we can have the outcome of the memory segment from each P elements or different processor elements, so that can again be given to the control unit. So this is a very broad view of SMID structure. We'll soon explore the two types of SMID architectures. So coarse and fine, that we'll see, and this is in an overview that how the things are going to manage. One thing is very clear, that we may work out with multiple stream data, and instructions are going to be common, and we work with many processors, okay, multiple processors. Now obviously you may be interested to learn about the different other aspect of this diagram, or the different other aspect of working with the architecture stuff, so that we'll explore in the subsequent diagrams. Let me show you one example also. Like if you have been asked to draw about the general structure, how the things are going to work. So on the same manner, like suppose if we have this control unit, first of all, on the same part what I have discussed. So you may have a proper recap and you may have proper understanding also that how the things work. So if we have different processing elements, that is PE, and obviously you learn that in case of SMID, we'll have multiple, processes also. So let me name this PE1, and then you can have PE2 also. This is PE2 and so forth. Like suppose we have till PEN. So it depends on the structures, how it has been implemented. So the control unit, okay, it manages, it controls all, the processors, all the processing elements, and there may be different data streams. So we'll say DS, DS2, DS3, okay, and they may be connected to a memory segment. That is, we simply write a memory, and every memory may have its module, okay, memory module 1, which belongs to the processing element 1. We can have mm2 and so on, like this, so forth, mmn, and whatever results we are going to have, so that's maybe again given as a feedback levels for control unit, like this. So that can be treated as one of that structure for single instruction multiple data stream, where we take the control unit as a major part of how the things are going to be assembled, how the things are going to be merged, how the things are going to be context. Okay, so if you take if you want me to take one more example, like suppose, let me go to the next slide. If suppose we need to have a vector addition, okay, a plus b, and there are say 10 elements, okay, at the same time. So obviously for us, when you understand the vector processing system, so how does it work? So even if this has been traditional system, I have been simply saying that we are going to execute a loop, and the loop is 1 to 10, and then we can have the entire piece of code, whatever you write over here. But this is not the case. This is the traditional system. Okay, this is the traditional system. In case of vector processing, we can arrange like this: Ci is equal to AI plus BI, assuming that the value of you can say I is from 1 to 10, okay, is equal to less than equal to 1 to 10, the same way, and we can have the structure. Let me show you, because I have just shown this in the previous session. Let me show you in terms of this SMID structure, how it's going to be executed. So obviously, if you can say the control unit cu is there, and we have different PE elements. So we have PE1, what we have shown, PE2, say PE3, that PE stand for processing element. So processing element 1, processing element 2, processing element 3, element 4, and if it's more than that, now every processing elements may work out with for the instance, and this is going to be in terms of vector operand. So we can have A1, B1, C1, because if you can see, we are just going to have the 10 vector operands over here simultaneously. Okay, so we have A1, B1, C1, then we can have in the second memory A2, B2, C2, assuming that they are independent, then A3, B3, C3, and like that we can have up to the last one. If you just go through, if it is E10, so we can have A10, B10, and C10, and thoroughly we can have this in memory itself. So it can be shown as M1, M2, M3, M4, and obviously the results can be shown here. Okay, so this is just a broad level view that how the things are going to be managed in terms of once we have more than one processes and we are going to work with multiple data streams. Now, the very important aspect, students, that belongs to that what is the classifications? Okay, what's the classification of SMD structure? So as you can see in this part itself, that it may be of two types. The first is the fine-grained SMID, and the second is, we can say, the coarse-grained. So if you're referring the notes, please go through 10.4. You can have a better classification of fine as well as coarse grain. So these are the detailed description which deals with much smaller components. So this is the core of that, much smaller components which are in actual in composed of much larger components. Okay, so this is the streamline that we are going to work with much smaller component in fine grained SMD structure. And in coarse grained, these systems are consisting of fewer components which are obviously more than original but are much lesser than this. If this has been compared, so you can understand they are much more with compared to the original. So that's why the name given coarse grain, which is going to be very fatty. Okay, but the size of components is much more than the fine grained subcomponents of a system. Now, for fine-grained architectures, okay, they generally designed for low-level image processing applications. Okay, so this fine-grained they are defined for low-level image processing applications, and their complexity is minimal, and the degree of autonomy is lowest feasible in each processing element. I repeat, the degree of autonomy. Okay, so this again a very important point to be noted. Degree of autonomy is lowest. Now, there are different economic constraints that are applicable on the maximum number of P's, and it is assumed by the programming model that there is an equivalence between the number of P's and the number of data items. Fine. So based on this introduction, let me explore the many things about this, and we'll have a detailed comparison also about the fine grained and the coarse grained also. So what I said earlier, that the fine grained is used for image processing applications, and it has been started by NASA itself. Various examples, various structure exist over here. Large number of PEs, minimum complexity, and the programming language is a simple extension of sequential language in terms of software category. Now the coarse grained, each processing element is of higher complexity, and here you can see it is the minimum complexity, it's higher complexity, and it is usually built with commercial devices. And the most of the point that is going to be very important, that each processing elements has local memory in terms of coarse grained. Let us explore some other examples also through which you may understand. So one of the very important aspect of working with the SMID architecture for the first category, that is massively parallel processing. As you can see in the system itself, that there may be memories which may be connected through the message bus every processors, but they consist of coordinating processing of a program by multiple processors that works on different parts of the program, with each processor using its own operating system and memory. Okay, this has been very relevant in once 80s. Before that, before we come to the modern systems, and still there have been different processes that has been implemented this kind of structures. As you can see in the second point also, that massively parallel processing is an array of independent processing nodes communicating over a high-speed interconnection buses. Now let us explore how this can be used. But before that, I wish to show you of very of the model which I have taken from this computer history. As you can see, the manufacturer where DEC, which stand for Digital Equipment Corporation, and you can see how it look like in terms of the VAX 11/780 computers in terms of the mainframe category. So as you can see, this was introduced in 1978. Okay, how it looks like, because the modern day we understand that computer belongs to this category, computer is of this type. So you may also go back and you can see the history. So there have been very interesting stuff. Okay, although we are limited with the time constraint, but do understand that from the journey, from where the journey begins and how the commercial things has been violated also. So this dimension is of 60 into 48 inch into 30, and the manufacturer, what I said, it's Digital Equipment Corporation. Now this wax has been used over here, and in terms of that, you can see if we have a large array of processors, so we may have two memory instances over here. The first may be this input and the output memory, which may be implemented through a form of registers, and there will be a switching element because there is a huge number of processor array, and each array is can multiplex with n number of other switches or hubs, because that kind of stuff has been implemented with this. And there's a one staging memory which is again connected through the switch part. So I repeat, number one is we talk about this processor array. Although there have been different variation for this also. Now if you come back to this controller part, so again the same machine what has been shown through the MPP, that is virtual address extension 11 by 780, what I have shown in the previous term. And there may be a common database or common storage, but apart from that, each processor array which is the part of this diagram may have its own share of memory also. Now there may be staging memory, again very important stuff, and this is the overall structure of fine-grained SMID structure, and it's implemented by default the MMP system. Now just next to that, I wish to show you the coarse-grained SMID. So when I will just come to the next part where I'm going to discuss with various algorithms. So you various differences. So be very clear about that in coarse-grained, where the things are going to be very fatty in terms of the name itself. So we have this Spark microprocessors, we have different vector units, and these vector units are particularly designed for floating point, we can say units. So let me write this also. So once you have this 64-bit bus, although I have just taken this example according to the contents of yours, it's a 64-bit bus, but there have been different variations of this topologies also. So data interface, and we have this data network, and there will be control interface, which we move to the control interface, and there will be different segments of memory. So here we are taking the 32 MB memory. So what is the logic that if you are going to work out with the floating point numbers, because it requires large array of computations in terms of the numbers, so we have different vector units available over here, and this has been connected through a common 64-bit bus, which has been interlinked with the microprocessors, which has been with data interface and the control interface. All right, now based on this, because I think we have still left time. Yes, so based on this, I have shown that the first one, the fine-grained system, we have talked about the part of memory, how it's implemented. We also talk about this registers, input and output, and the switching elements, and this virtual address extension also. Now this is fine grained, and the second is coarse grained. Now because you have seen the diagrammatic point of view, so it's better, let me go through this the differences between both also. Then you will have a clear understanding of how that can be differentiated in terms of processing, in terms of capability, in terms of many other things that may refer to. Okay, so I come to this part. Fine grain, the first one. So this talk about fine grain, and the second is coarse grain. So fine grain has less computation, what we have discussed in the first part. Scalable. Okay, next processor. And this coarse grain have more computation time than the fine grain architecture. The first parameter in terms of timing, this coarse grain have more timing with compared to this fine grain. Now, in case of that, let us see the granularity, okay, in terms of the programs. So programs are broken into large number of small tasks, okay. So we have this structure that there has been large number of small tasks. This has been executed. And here in coarse grain, programs are broken into small number of large tasks. So the program is small, number is small, okay, but the capacity, the large task. As you can see, the tasks are small and the tasks are large. Okay. Now I don't have any specific criteria to speak about over here, that how the exact you can if you may ask me, so what is the granularity component over here? So simply we understand this in terms of small and large according to the functionality. Now fine-grained SMID have much higher level of parallelism than coarse. Very important point, okay? Because if I will ask you what's the reason behind this, so the reason is this. Let me go back to the diagram, and you can see this is the reason. And we are not constrained towards this only. There are lots of other extensions also for this processing array. So the third point is the coarse grain SMMD has lower level of parallelism than fine grained. Now grain size is over 1000 instructions, and here the grain size in range of 2 to 500 instructions. Okay. Now here the size of some components is much smaller than the coarse grained, already discussed, and here the size of the subcomponent is more than the fine grained. Now, two types of parallelism can be obtained. The first is instruction. I hope you may be comfortable with this. Then we have discussed that there may be ILP, instruction level parallelism, or data level parallelism, or different aspect of like loop. So two types of parallelism we can achieve, that may be of instruction level and loop level parallelism. And the second case, in case of coarse grained SMID systems, we can have parallelism in terms of subprograms, or we can have a much higher level of program level parallelism. In continuation with these differences, we also need to focus on this, and you may also have a search by your own. You can do also some sort of more investigation once we'll talk about this, that CM. Okay, CM1, CM2, there are various examples. So as you can see, the connection machine, also into limitation of time, and as per the syllabus, I'm not going through the extension of all these examples, but if you wish, you can always refer in you can find it out more about this, that connection machine to J machine, they belongs to fine grained, and we understand gray and Y, they belongs to coarse grained SMID structure. Now let us complete this, that in fine grained load balancing is proper, because that kind of control mechanism has implemented in terms of hardware structure, in terms of software structure also. Now in coarse grain SMID, load balancing is always has been issue. And if you have been, if you have any working knowledge of working with distributed environments, this is a very important factor in terms of different structural view, that load balancing, how to make it, on a justifiable node. So as you can see in both examples, in the fine grained system, this load balancing is found to be very, authentic and proper. And in case of this load balancing, the second part, that is coarse grained system, the load balancing seems to be an issue. Now here, parallelism can be detected using compiler. Okay, and in the second category, parallelism cannot be detected using compiler. So you may be wondering that how come the compiler is going to detect this. So obviously just upper to the part of operating system, if you are executing the different system softwares, so compiler category can be implemented in such a manner that it can see what is the level of parallelism that is executed. Okay, but every time it's not possible, and this compiler, why it's getting that, it also depends on the structure that we have discussed in the previous we can say slides. The next point is this: fine grained SMID is a much costlier process than coarse grained SMID because of the structure, and this is much cheaper than this fine grained SMID. Now, fine grain is concept of future multi-threaded architectures to be used also in various other approaches, and coarse grain is one of the earlier concepts of single-threaded architecture. So that's why this has been limited to this category or this part only. Now, the detailed description is further divided into many small subcomponents and makes the processes less complex from the original one and from the coarse grain also. And if we can come to the second part, that is the detailed description is divided into large subcomponent, that was the definition point of view also, and makes the processes so it makes the processes less complex than the original one. Okay, but if you can just see, it's more complex with compared to fine grain. Already we have seen the examples we have discussed, that connection machine 1 or J machine or Cray, and there are so many examples. So by this we come to the summary of our session, where we have explored the SMID structure, and we have also explained the types of SMID in terms of fine grain as well as the coarse grain. So overall, as you can say, that parallel processing is one of the very important and integral aspect of our everyday life also. There has been a lot of instances we can find it out, that parallelly, like suppose if you move to a car washing center, you can find it out. If suppose first job has been done, so it is sent to the second task until the first tray is empty, we can have the second car also. So there are lots of example in everyday life also. So this parallel processing can be established by dividing the data among different units and each unit being processed simultaneously. Okay, that's the core of everything. And the time and sequence, they are controlled, they are executed, they are governed through the control time to get the fruitful result, okay, in minimum amount of time. And the very important part is that the core element, okay, if you can refer, the core element of parallel processing is CPUs. Okay, that's why, we used to say it's a true parallel system. What's the reason behind this? We need to make it on that level also, because it's not only concurrency, it's all about parallel system with concurrency. So the essential computing process is the execution of sequence of instruction on a set of data. And as we have seen that if there's a single instruction, so what does it mean? It implies that all processing units execute the same instruction. Okay, execute the same instruction, that is I, on a same clock cycle. That's very important when we say that the term single instruction. So we should be very particular about that. What is single instruction? It means that all processing units, either it is P1, P2, and so on, they are execute the same instruction at any given clock time. So this was the basis of everything, and modern superscalar SID machines exploit a property of the instruction streams, and particularly they employ ILP, that is instructional parallelism. So we'll keep continuing this charm. We'll keep continuing the discussion in the subsequent sessions also. So let me summarize the things that in this topic you have learned about the concept of data parallel architecture. And if you can see in the very beginning, I have discussed about the design space and design issues in terms of software category as well as hardware category also, where we have discussed about the environmental features, the maintainability, the scalability, and very important features. We have also discussed the types of SMID architecture and fine-grained and coarse-grained. And apart from that, we have also have so many differences also between fine-grained system and coarse-grained system. So all students, I thank you all for being so active learner. I wish that you may have a recap whenever you feel that you need to go through more detail. Definitely, you can refer the contents which has been provided to you. You can have a view recap of the video, and also definitely if you want more differences between fine and coarse, you can refer the contents what we have discussed. So this session was the overview of working with the SMID structure. In the subsequent session, we'll see more type of parallel architecture. So with this, I thank each one of you, and let me go through if there is any point of discussion from your side. Again and again, and you will find it out more context. Thank you so much, and over to you, ma'am.
Thank you, sir, for such an informative session.
Yeah.
Now, if the learners still feel any doubt, they can post it on the discussion board. Have a nice day, everyone. Thank you.
Thank you, ma'am.